All right, so key features here, boys, is that a Bernoulli sequence is got a few key attributes, okay? So a Bernoulli sequence is defined as a experiment that is has only two outcomes, success or failure, and we can consider success as rolling a 6 or not rolling a 6. So there doesn't have to physically be two separate outcomes. We just define them as two different outcomes. So the Bernoulli sequence has success or failure, and more importantly, the probability remains the same for each trial. Okay, so if we're doing sampling out of a bag, that kind of thing, it's always going to be with replacement. So if we consider example 2, which is a typical probability sort of question that we looked at last chapter, our netballer is going to shoot a goal or not shoot a goal. So let's just change that. So she gets a goal or she doesn't get a goal, and she's going to have two trials. So it's goal or not goal. Or not goal, yeah? And the probability of getting the goal is 2/3, which means the probability of missing is 1/3. And that doesn't change. So then the question they want is the probability that she will score one goal from her first two attempts. So attempt 1 is the first column, attempt 2 is the second column. So for her to get one goal, it means that if she gets a goal on the first shot, she misses on the second, or a goal on the, she misses on the first shot and gets a goal on the second, which gives us 2/3 by 1/3 plus probability of not getting a goal is 1/3 by 2/3, which is our 2/9 plus 2/9, which is 4/9. Okay, so that's a typical kind of example that we had last chapter. So if we now talk about a binomial distribution, it is really just another name for a set of Bernoulli trials. Okay, so for a binomial distribution, key features: n independent trials, 2 possible outcomes, and if P is the probability of success, 1 minus P is the probability of failure, which we sometimes represent as Q. Okay, so what we do, because it's a distribution, we have a variable X, and X represents the number of successes. So if I toss a coin 3 times and I want to count how many tails I get, I either get 0 tails, 1 tail, 2 tail, or 3 tail. And that's X. So X is the different number of successes that our distribution can take on. All right. So to formally define our distribution, obviously we have n trials and we have probability of P for success. So for our binomial distribution, we write that statement each time we have a problem. X is distributed as binomial, whatever the number of trials are and whatever the probability of success is, we list those. And they give us a rule, okay, or that gives us a rule. All right, so if we break the rule up into parts, NCX, that's the number of combinations that we have of X successes, okay? P to the power of X is the probability of getting X successes, and 1 minus P is my failure. So if I have, for example, 10 trials and 3 successes, I'm going to have 10 minus 3, which is 7 failures. Okay, so that tells me the number of combinations. This gives me the probability of one of those combinations. All right, so X is the number of successes out of n trials. All right, so let's have a look at this example here. All right, so we're going to have probability of success is 0.2, and we're going to have 10 people. So in this case, X is distributed binomially, 10 trials, and the probability of success is 0.2, where success is getting a left-handed person. So here, exactly 3 people will be left-handed. We want the probability that x will equal 3, which is equal to 10 trials. I want 3 successes. The probability of success is 0.2, and I need 3 of them. The probability of failure is 0.8, and I need 7 of those. Okay. So if we use our calculator, and I might come back and fill in these actual values later, but that will give us the probability of getting exactly 3 people, 3 left-handed people. If I want to get the probability of at least 9 people will be left-handed, well, at least 9, what does that mean? So the probability of at least 9 is a probability that x is greater than or equal to 9, which means I get the probability that x is equal to 9 left-handers plus the probability that x is equal to 10 left-handers. Yeah. So what is the probability of getting 9 left-handers? Well, out of 10 people, I want 9 left-handers, which means I get 0.2 to the power of 9, and I get 1 failure, or, and an or is a plus, out of 10 people, I choose 10 people, which means I get 10 successes and 0 failures. Okay, what we actually find here, though, I think that one from memory is about 0.0004, and this one is basically 0. All right. Finally, more than 1. What is more than 1? So the probability of more than 1 is x is greater than, what if we put x is greater than or equal to 2? Because more than 1 means you can't have one person. So it's got to be either 2, 3, 4, 5, 6, 7, 8, 9, 10. So instead of counting up all those, what if we do 1 minus the probability that x is less than or equal to 1, which is going to be the same as 1 minus the probability that x is equal to 0 plus the probability x is equal to 1. Okay, it's quicker than working out all those other values. So for us, 1 minus x is equal to 0 means I have 10 selections, I have 0 successes, I have 0.2 to the 0 successes, and I have 0.8 to the 10 failures, minus, well, out of 10 trials, I get 1 left-hander, which is 0.2 to the 1, 0.8 to the 9. So I have 1 success and 9 failures. So if I'm obviously out of practice here, lads, because I've just discovered I've done this whole page without any recording. So what I'll do is I'll just briefly talk over some of the key things that we've done. Obviously, example 4 is very similar to what we've done previously. 8 trials, probability of success is 1/6. Continue to use your binomial rule. So 8 trials, 0 success, 1/6 to the 0, 5/6 to the 8th, okay? And possibly we can get some decimal values there if I had access to the CAS. Only 6s means 8 out of 8 trials, 8 out of 8 6s. So x is 8 in that case. The first is a 6. All right, well, the probability of the first one being a 6 is just 1/6. And then if the next 7 are not 6s, well, we can probably do that without using our distribution. All right, just means the next 7 attempts are all not 6s, which is 5/6 by 5/6 by 5/6, which is 5/6 to the 7. As opposed to D, which is similar in that we only want 1/6, but it doesn't matter where the 6 occurs. And that's what the 8C1 does. Okay, you can see the 1/6 to the power of 1, 5/6 to the power of 7. That's the probability of getting 1/6 somewhere or in a specific spot. The 8C1 tells me how many different arrangements I can have to get that 1/6. All right. Example 5, guessing correct answers on a multiple choice test. Sounds something some of our students might have done. Again, very similar. Get half of them correct, but we have 30 trials. We want 15 correct. The probability of 1 correct is 1/5. The probability of getting it wrong is 4/5. So we just add the values where we need to be. At least 1 correct, we're not going to do 1 plus 2 plus 3 plus 4 plus 5, etc. up to 30. That's the equivalent of 1 minus getting none of them correct. And so the probability of getting none correct is just x is equal to 0. So 30 C0, 1/5 to the 0, 4/5 to the 30. All right. Obviously, in this one here, you're going to have to pause it a little bit so that you can write the information into your booklets. I touched briefly on using the calculator, and this is by far and away the easiest way. All right. So the key is to remember that the PDF, all right, is if we have an exact number of successes, i.e., we have 3 correct answers, we have 3 left-handers. All right. So it's an exact number. The CDF we're going to use if we have a range of successes, so an inequality, if x is greater than or equal to 1 or x is less than 10. All right, so you see here, x is equal to 15, we've got a PDF. 30 trials, 0.2 success, 15 successes, get an answer. All right, as opposed to the rest of them are all inequalities. All right, so we're going to use a CDF feature, and less than or equal to 3, I have 0 to 3 successes. Strictly less than 3, well, that means the most successes I can have is 2. All right. Greater than or equal to 10, I've got 10 to 30 successes. As opposed to strictly greater than 10, the little minimum I can have is 11 to 30 successes. Finally, the last question is a little bit different in that it talks a little bit about conditional probability. So A given B, it's a rule from last year, is equal to the probability of A intersection B over the probability of B. All right. So if we apply that to this scenario here, what's the probability of x is greater than 5 given x is less than or equal to 10? Well, it's got to be x is greater than 5 and x is less than 10 over the probability that x is less than 10. All right, so that's our rule. So the top line simplifies to values that are greater than 5 and less than or equal to 10, which means we want the numbers that are greater than 5 and less than or equal to 10. So that's the interval that we want. Over again, the probability that x is less than 10, which means we go to a binomial CDF, 30 trials, 0.2 success. If I want to have greater than 5 successes, well, that's 6, but less than or equal to 10. So I want to go from 6 to 10 over x is less than or equal to 10, which is from 0 to 10 successes. Okay, so look, sorry about that. That's a little bit of a brief rundown of what we did through there. Hopefully that clears that up and you've looked at this over the weekend. And yeah, we'll pick it up on Monday.